What do the first and second derivatives say about a function? Our objective today is to specify intervals of increasing or decreasing for a differentiable function. We'll use the first derivative to find local max and local mins as they exist. We'll also use the second derivative to identify inflection points and intervals of concavity, which determines the shape of the function. In short, we'll implement first and second derivatives to describe our differentiable function. Now, our first example is a picture, and a picture can sometimes represent 1,000 words. We'll focus on the first derivative for now, and primarily the first derivative is used to identify extrema, local and or absolute. So notice that we have 5 critical numbers in this following diagram, and they're located here on the x-axis. Now, if you describe the function relative to the critical numbers, then we want to analyze the slope of the tangent line evaluated at that critical number. So notice the slope of the tangent line evaluated at this first critical number is 0, but that doesn't necessarily indicate a local min or local max. And that is because the function was increasing in the interval before the critical number, and the function was also increasing in the interval after the critical number. So be aware of how the function increases and decreases, and that will help us determine whether or not we have a local max or local min at a critical number. So C1 is a critical number, and f of C1 is not a local max, and f of C1 is not a local min. As I was describing earlier, the function increases before the interval that has C1, and then after the interval that has C1. I'm sorry, after this interval right after C1. Now let's look at C sub 3. C sub 3, however, is a critical number, and f of C sub 3 is a what? Just by observation here, it is definitely a local minimum. So what you want to do here is write local minimum, practice the vocabulary, or you could at least just say local min. How about C sub 4? C sub 4 is a critical number, and the derivative of f of x at C sub 4, however, does not exist because this is a corner up here, and a corner, if you look at the slope of the tangent lines right before and then right after, they do not match, and so the derivative of f of x at C sub 4 does not exist. However, f of C sub 4 is an what? It is an absolute max. It is the highest output value for the entire function on the interval AB. It's also a local max. It does satisfy derivatives before that critical number, and there is a derivative after that critical number, and so that's what helps it to find that output value to be a local max. Remember, max and mins are always y values. When we say f of C sub 4, this is a y value. C sub 5 is a critical number. However, it is not a local what? It is not a local min. Oh, it's also not a local max. at x equals a, just by using the extreme value theorem, we can see that has an absolute min. Specifically, the absolute min is f evaluated at a. So notice every little symbol here represents a little bit more of the story or a little bit more of the big picture. It's very important that you're able to recognize the open intervals. And we're going to use this later on as a number line test. So we want to be able to specify the open intervals, and they're usually separated by critical values or critical numbers. So there's actually 1, 2, 3, 4, 5, 6 open intervals, and we basically describe functions and we analyze functions one open interval at a time. The intervals are listed right there, just being able to list it in the picture and list it as pros. Now, on the interval here, C1, C2, right there, this open interval, we can see that the function is actually increasing. And we denoted it down here with the symbols. Okay, we can see that on C1, C2, the function is increasing. And then from C2 to C3, on this open interval, the function is decreasing. So that is very important in the study of graphs and models. We want to know when the output values are increasing and when they are actually decreasing. And if it behaves like this before and after a critical number, then we could actually conclude that f of C2 is now a local what? It is a local maximum. So every detail counts, every symbol counts, every open interval is going to count, and that's how we're going to describe the shape of a differentiable function. Is usually one open interval at a time. The first derivative test is basically summarizing the picture that we just analyzed. Make sure you're able to read this very carefully. Make sure you understand what it says. But ultimately, we'll view an example to see how testing is going to be so important. You're basically going to choose your own appropriate test values, and you're going to test this first derivative one open interval at a time. The first derivative test obviously involves critical numbers, and then let I be an interval containing C. This is not the interval that we're going to be interested in, but this is going to be necessary so that we look locally around C. And so that's what helps us determine whether or not we can seek a local min or local max. So if the first derivative changes sign from positive to negative around C, meaning before in the open interval before C and in an open interval after C, then f of C is a local max. Similarly, if the first derivative changes sign from negative to positive, once again in an open interval before C and an open interval after C, then f of C is a local min. Once again, choose your own appropriate test values, and testing the first derivative with a drawn number line really helps. Okay, if the first derivative does not change sign around C, once again, before in the open interval before C and in an open interval after C, then f of C is not a local max and f of C is not a local min. And that was the earlier picture. So if you go back and look at that earlier picture, you're going to realize that's describing a lot of the first derivative tests.